Yes. Let me just switch to present. Cool. Do you see my screen the way it is?
All right, perfect. Hello, everybody. Welcome to another Launch and Learn. My name is Xiang. I see a lot of familiar faces and some new faces saying hi in the chat channel. Hello, Alice, Gavin, Joshua, Owen, Harry. Today, can everybody see the screen all right and hear me all right? If so, please type a yes, so I can. I'm sure like audio and video are working fine. So today, okay, perfect. Thank you. Today we have Andrew to give us a talk on GANs. That stands for General Adversarial Learning, and also a little bit about adversarial learning in general. So Andrew is a data scientist. He is currently leading the data team at Lucca. Andrew will talk a bit about his company and what Lucca does. They use deep learning to make great design accessible and delightful. Andrew has worked as a data science for over 7 years, delivering individually catered solution to business critical data problems. So now I will give the mic to Andrew, and Andrew, give it away.
Thank you, Xian. So for this presentation and this lunch and learn, I want you guys to walk away with an idea of where GANs fit into the pantheon of generative models and an understanding of how they work, and also just where to take it next and some of the places these really exciting models are going. So, to begin with, I'll just show you some images that have been generated from GANs and an idea of how much progress has been made in the last 4 to 5 years. So these are unconditionally generated ImageNet samples taken from a model called Big GAN, which was presented by Andrew Brock at iClear this year. And these generated images are of really surprising and really impressive resolution. And they also cover a large number of different classes. You have an animal, you have a mushroom, you have food, you have a scene, all generated together. But it wasn't always like this. This is an image from the original GAN paper, the original Generative Adversarial Networks paper by Ian Goodfellow et al. And that came out in 2014. And at this time, the state of the art in image generation was nothing like it currently is today. The data set that we're generating samples from here is the Toronto face data set. And you can see that the images are very low resolution. I think they're 32 by 32. And the features aren't resolved very well. They're still kind of fuzzy. Now fast forward 4 years, and this is a paper out of NVIDIA called StyleGAN. And these generated humans look like they could be real. I would challenge people to mix these faces in with faces of real people and see if you could tell the difference from them. So this is a thread that's going to be running all the way through this presentation, which is GANs and generative models more generically have been improving at a very impressive rate, and the breadth of applications for these techniques are constantly increasing. So before I dive into the presentation on GANs and adversarial learning, I'm first going to tell you a little bit about the company I'm with. We're called Lucca. So Lucca is a graphic design platform, and we want to create the experience for users that they're working with a graphic designer while they're on our platform. So right now, the way we work is users come on. Usually they're looking for a logo, but they might also be looking for business cards, social media kits, or a website. And we generate designs for them based on what they tell us about what they want. So for instance, a user will come on, tell us the industry they're in, show us some designs that they like, tell us the colors that they want, and we'll start generating designs for them. At this time, we're focused on logos and business cards and websites. Everything that a business needs to get started, to get off the ground. But the development direction we're taking is to offer a general purpose graphic design solution for small businesses and just users who need an affordable way to get terrific design. So just a few more details. We were founded in 2016, so about 2.5 years ago. Our office is in downtown Toronto. We were lucky enough to host some of you on July 2nd, when my colleague Reza gave a terrific presentation on subscale pixel networks, a kind of autoregressive generative model. The company is 40 employees right now, and we've recently raised a Series A, so we are actively growing. And we have a large number of users. Over 1 million have used the platform, and we've sold well over 150,000 logos. So there's a really interesting business there as well. And currently we're hiring for software and data engineers. Now, this topic of GANs is very important to me because it ties into a lot of the work that I do here. A big portion of what my team does is we work on creating generated content. So this means we're not just generating designs for users, but we're generating the elements that make up those designs. So the two big areas we're focused on right now are generating typefaces. And on the left here, you'll see some of the imaginary fonts, but they're actually very real. They're just not human-made, they're computer-made. And on the right, you'll see some of the symbols that we've created through generative techniques. To date, we've sold almost $15,000 worth of generated symbols, which would make us, as far as I know, one of the first companies to actually be leveraging generated content for revenue. So we spend a lot of time working with generative models here, and GANs are part of that arsenal that we employ every day. So now, without further ado, let's get into the presentation. So today's itinerary. First, I want to show you how GANs fall into the family of what we call generative models. Then I want to dive deeper into GANs, looking at the training, looking at the architecture, looking at the relationship between the discriminator and the generator, because there's a lot of very useful concepts that can and have been taken out of analyzing how GANs work. From there, we'll go and discuss a few of the really interesting applications of GANs, even though there's a large number that we're not going to cover. And then go to the challenges of GANs, because with GANs, the theory is very nice, and on paper, everything seems very easy and nice to work with and clean. But then once you actually go to implement them, things aren't quite so simple. So we're going to talk a bit more about that. And then finally, we'll look at what's coming next and some opportunities in the future. So generative models. At first blush, when we're talking about generative models, we're saying we want to model the distribution of a given data set. And with the generative models that we're talking about today, that data set is usually a set of images, but it could also be, for instance, a set of audio samples as well, or a set of time series data. But what we want to do is just get a model of this distribution. This can be done implicitly or explicitly. GANs are an example of an implicit generative model, while autoregressive and variational autoencoders, which we'll talk about briefly in a moment, are examples of explicit generative models. The difference being that with an explicit generative model, you have the probability density. With an implicit generative model, you have to sample in order to really get a sense of what that density is. You don't have it there at your disposal. Now, when we're evaluating generative models, one way to do that, and that looks very good in papers, is to sample from our model distribution. And by visually inspecting the samples to see how well they match up with our original data set, we can start to get a rough way to evaluate how good our model actually is. And really across the board, these generative models have seen tremendous improvement over the last 5 years. So in a deep learning context, when people are talking about generative models, they're usually talking about one of 4 kinds of models. There's autoregressive, there's reversible, there are variational autoencoders, and there are GANs. Now, GANs are the only implicit generative model here. The other 3 are explicit. That means we can train them with some kind of maximum likelihood, and they give us a probability density that we can work with after training. Now I'm going to take a brief look at each of these kinds of models. So autoregressive models, they are a class of generative model, and we'll talk about images for this just to keep it consistent across the 4. The way autoregressive models work is you generate a pixel conditioned on the previous pixels that you've generated. So when you're generating an image, you generate it pixel by pixel. Now, autoregressive models were proposed in about 2015, 2016, and one of autoregressive models for generating images were first seriously proposed in about 2015, 2016, with the pixel RNN and pixel CNN models coming out. These models were attractive to people because you had the likelihood estimate as a measure of how well your model represents the data distribution. On the left side, you see images generated from the Pixel CNN paper, which came out in 2016. And on the right side, you see the images generated from the subscale Pixel Networks paper published in 2018. So you can see, just comparing those two, that there's been a lot of progress on this field. The images are much crisper than they were before. A challenge with autoregressive models is it does take a long time to generate these samples, and the subscale pixel networks model is a very computationally intensive model to use. Now, reversible models. So reversible models will make a little more sense to you once we dive into more detail with with GANs. But the concept of a reversible model is we can take the idea of a GAN and we make the generator reversible so that we can pass images and noise both ways through it and go from noise to image and image to noise. Now, these models haven't received as much attention as some of the others. One of the early ones was made by Din et al. In 2014, and it's called NICE. And it really, recently, there's been this model from OpenAI called GLOW, which uses one-by-one convolutions to get very nice results from reversible models. But there are still some drawbacks in terms of the likelihood estimates aren't as good as you would find for variational autoencoders or for autoregressive models. But on the plus side, the sampling is much more efficient than autoregressive models. Now we get to variational autoencoders, and these were proposed in 2013 by Kingma and Welling. And on the left there, you see a sample manifold. So this is kind of, you could imagine it like a section of the latent space. And variational autoencoders are nice because, again, they're explicit. Unlike autoregressive and reversible models, you train them approximately. You don't have this tractable formulation to work with, but you can train them very efficiently. And for a long time, variational autoencoders had the big criticism that the results, that the samples that came out of them were very blurry. And up until very recently, this has been a valid concern. However, a paper that came out very, very recently is called VQVAE2. It's by some authors at DeepMind. You'll see the results of it on the right here. Show that under some circumstances, this criticism is no longer founded. And now, after traversing all the other generative models, we get to GANs. And GANs stands for Generative Adversarial Network. On the left here, you see those Toronto face dataset images that I showed earlier, which came from the first GAN paper, which was by Ian Goodfellow. And on the right, you see those style GAN images from NVIDIA by Karas et al. And GANs, like I was saying, are the only implicit generative model that we're talking about here. And that means that if we want to see how good of a model we have of the distribution, we have to sample it. Now, GANs create very sharp samples, which is very appealing for a lot of reasons. But the training of GANs can be finicky. And GANs are also susceptible to something called mode collapse, where you don't capture all the modes of the original distribution. And sometimes you might not know that you're not capturing all the modes of the distribution. So there's a lot of really cool challenges associated with GANs that we'll touch on a bit at the end of this presentation. But first, I just want to build up your understanding of them and how they work. So we'll go into an overview of GANs. Now, this is a quote from Jan LeCun, one of the pioneers of, I guess, gradient-based deep learning, and what's it called? A co-winner of the Turing Award this year, which he shared with Jeffrey Hinton and Joshua Bengio. And this is just to indicate that there's a lot in GANs, and there's a lot to unpack, and there's a lot to learn that we can apply to other areas of machine learning than just, say, image generation. So, how does a GAN work? With a GAN, we have two networks. We have a generator and a discriminator. The discriminator is trained to identify generated examples and distinguish them from real examples. So we start with a data set of real examples, and we want to learn the distribution of this data set. So the discriminator is trained to identify whether a sample comes from the real data set or whether it comes from the generator. Now, what the generator does is it takes random noise and learns how to transform that random noise into realistic looking samples. So over time, what we want to happen is the generator gets better and better at producing samples that look like the real examples, and the discriminator gets to a point where it's making random guesses as to whether a sample was real or generated. We can think of this like a two-player minimax game, and this point where the discriminator is making random guesses is where they have their Nash equilibrium. So going into the training just a bit more, what the generator is learning is how to transform random noise into images. It takes samples from, usually it's a Gaussian, takes samples from a Gaussian, transforms it to this neural network, and then creates a sample, and we want this sample to look as real as possible. So this is part of what's so intriguing about GANs, is this is such an elegant formulation where you have two networks in a completely unsupervised setting. You can add labels to GANs and you can condition them, but they also work totally unsupervised. And due to the dynamics created by the loss function, they're learning how to generate great examples. I'm getting some feedback on the audio right now. Did anything change, Jan? Thank you. Right, so the discriminator is trained to identify which samples come from the training set and which come from the generator. And the generator is trained to generate samples that trick the discriminator. Now, the dynamics of a generative adversarial network are mediated through the cost functions. So the discriminator has its own cost and the generator has its own cost. And the fact that we have two different cost functions creates some of the challenges in training that we'll see later. But it also enables this really wonderful unsupervised learning to happen. So the discriminator cost is it wants to correctly identify real samples as real, and it wants to correctly identify generated samples as generated. So you can see that on the left here, where the first term is saying we want to identify real samples as real, and the right term is saying we want to identify generated samples as generated. So now the cool thing here is that the generator cost is just the negative of that. And you'll see here we have a constant where where it's referring to the discriminator identifying real examples as real, because the generator is not directly concerned with that. What people found, if they use the loss function for the generator as it is in the top equation, is that the loss saturates. So that means if the discriminator is very confident that the generator created a certain sample, going back to it, so it's hard for it to update to actually get better. So what we do is we just change the formulation a bit. We have this equivalent way of writing it on the bottom, where now the generator gets very strong signals if it creates samples that the discriminator easily identifies as generated. So by using the second equation, it isn't exactly a two-player minimax game formulation anymore, but the training performs as we would hope it does, and the training is a lot more stable than it would otherwise be. Here's a nice graphic showing, yeah. How about at the end of this section, we'll pause. Uh, so, right, so this shows the training of a GAN model in a really simple way. We have in black the real distribution, in blue the discriminator function, in green the generator distribution, and the arrows show the generator function. So in the first pane, we have our generator function, our generator distribution way off the real distribution. We pass some samples through the model. The discriminator updates in the second pane. The generator updates in the third pane. And then by iterating that over time, we get to the last pane, which shows that state of equilibrium where the discriminator is randomly guessing and the generator is giving a good approximation of the true distribution. And to get specific for a moment, the original formulation of GANs by Goodfellow et al. In 2014 had some limitations to it, and the samples that it created were limited in resolution. The training was quite unstable. There was mode collapse. So there was a lot of work done by other researchers to come up with a more stable architecture for GANs. And I'm showing you a DC GAN right here, which is the deep convolutional GAN. And that was proposed in Radford et al. In 2015. And the deep convolutional GAN is inspired by fully convolutional networks. So whereas Ian Goodfellow's GAN was a multi-layer perceptron, DC GAN uses transposed convolutions all throughout the generator, and it uses batch norm between transposed convolutions. And this led to the ability to create larger samples with much more stable training. And DC GAN really kind of is the foundation of where a lot of GAN research has gone since then. So, Xian, you had some questions.
Yes, we have a few questions in the chat channel, so I'm going to relay them now. The first question is from Werner. Can you clarify more explicit versus implicit? What property is explicit and what property is implicit?
Okay. So for explicit versus explicit, with explicit we have the probability density. We have you can think of it like we have P of x, y, so that we can go in either direction and we can model kind of all the variables from that distribution directly. With implicit, you can think of it like the probability density function is a black box, and we can just take samples from it and get a sense of what that is through taking samples.
Okay, perfect. So, how are GANs different from neural style transfer?
So GANs can be used for style transfer, and that's something that we'll touch on later in this section, actually, in the application section. But they do have a lot of concepts that are complementary, and particular if you look at the style GAN paper, the Karas et al. One, then that shows really a good way to harmonize the concepts of neural style transfer and GANs together.
We have two questions about from noise to phase. So Owen asks, how, is the for each random noise has a so does each random noise have a corresponding real image? Is that how it's being trained? And Shahana has another question: is how does noise learn the feature of a face?
Okay. So I think I can answer both of those at the same time. So I'll go back here. What we're doing with the generator is we're starting with the noise and we're applying transformations to it as it goes from the beginning of the generator to the end of the generator. So initially, those transformations really are totally meaningless. They don't help it at all. So you would pass the random noise through the generator, and what you'd get on the other side would look a lot like random noise. It would look like that image that I showed earlier, just of the grayscale dots. Now, when you generate that image of grayscale dots and you pass it to the discriminator, most of the time, the discriminator is going to say, this doesn't look like a real example. I can clearly tell that this came from the generator. So then, using backpropagation, you get a signal sent through the generator that tells the layers in the generator to update their weights to say what you just created wasn't good. And then through this process, you pass some more random noise through, create an image, pass that to the discriminator. Now this time it might get tricked because just due to the nature of randomness, it had some features in it that resembled the real data set. So now the gradient gets a signal or the generator gets a signal that says, what we just did was good. And they update their weights based on what they just did was good. So by doing this through many, many iterations and with very large numbers of images, you slowly get the generator weights being updated in such a way that they can take random noise and turn that into a realistic looking image. So to touch on the first question, it's not like a supervised setting where you have a mapping of noise to image at the outset. You have your images, and then you just have noise coming from, say, a Gaussian. And through consistent attempts of the generator to transform that random noise into something that the discriminator will think is real, you gradually get a deterministic function, which is the generator, that can take noise and turn it into a realistic looking image.
Okay, perfect. We do have one more question, but it's about a workshop. I don't think we have talked about a workshop yet, so we'll leave that for later. So, okay. Andrew, please continue.
And how am I doing for time?
We're at 12:34.
Okay.
So, yeah.
Cool. If it's getting close, just let me know.
Okay.
So now we're going to dive into some of the applications of GANs. So one of the early identified applications of GANs, you can see in Ian Goodfellow's original paper that he shows interpolating between the numbers 1 and 5 of MNIST, is representation learning. Because through training a generator and discriminator, we can learn a latent space of our original data set. So this image that I'm showing you, it comes again from the StyleGAN paper, but you can find similar images in many, many GAN papers that are out there. For instance, the DC GAN paper also has a similar matrix in it. So what we're seeing is with source A and source B is we're taking the features, we're taking the kind of structure from source A and we're taking the style of source A and applying it to the structure of source B. So you'll see the top left, we're getting glasses applied to different images. Or we're making the people on the left look like young girls or like young boys. So for those of you familiar with language models and things like word to vec, you'll know that you can do vector arithmetic. So you can take a learned representation of a word and apply it to semantically similar concepts and get something you would expect out of it. So this is similar to what we're doing here, where we're able to add glasses to someone, reduce the age of someone, make someone more bald, these sorts of things through our learned model. And this has a lot of applications in terms of just understanding how well we've captured a distribution. And particularly since images are very high dimensional data sets to learn, it gives us a way to start to assess how capable we are at learning extremely high dimensional data. Another example is image translation. And this is where the style transfer comes in. So I have two papers cited here. I have the CycleGAN paper and the Pix2Pix paper. On the left, we see some image enhancement being done by the CycleGAN. And on the right, we have translating images from one style to another. So we have segmentation for the street view on the left and real images on the right. And then for the aerial to map, we have a satellite image and the sort of like map image. Now, there's actually a really interesting thing that comes from this satellite image to map image. It's a paper that came out last year, and it's called CycleGAN Master of Steganography. And what happens when you train this kind of transfer with a CycleGAN is you can go satellite to map and map to satellite. But what people were finding was that they were creating things going from map to satellite that you couldn't figure out just by looking at the map itself. So the CycleGAN was actually embedding very high frequency data inside the map output so that it could recreate the satellite output from it. Now, in this context, that's sort of like the model cheating, but it brings up a really neat application of something like CycleGAN where you can imperceptibly hide data in a different image. So again, these are the models that you would use, you can use for style transfer. For example, you can take paintings and make them look like real life, or make a winter scene look like a fall scene, these kind of things. Now, there's also another host of applications, and I'm not doing them justice by this list here to any extent, but you can get a lot of use out of GANs for semi-supervised learning, which means you have a small number of labeled examples, and you have a large number of unlabeled examples, and you can use GANs to create these unlabeled examples. And you can train GANs in this fashion as well. And semi-supervised learning in recent times has shown results comparable to actual supervised learning for things like classification. There's a very interesting paper from Ian Goodfellow called ACAI, and there was an AISC presentation from it in March, I think, maybe February. But what we do is, in this paper, we're able to improve the results of autoencoders, particularly improving the interpolations in the latent space by adding an adversarial loss to the loss function. So the model itself isn't trained in an adversarial GAN-based way, but we do have this loss kind of normalization term that allows us to get much better results than we would otherwise see with it. Now, you can also get out of image generation, and you can do audio generation with GANs as well. There's been some cool work with like creating voice impersonations using GANs. Another example is there was a recently released Google paper. I think it's called Robust Neural Machine Translation, where they use they generate adversarial examples using a generator, and they use that to perturb the model to improve the results of the translations. So as people are getting more comfortable with the concepts of GANs, they're finding more and more areas to apply the learnings to. And you especially see with a lot of that work I was showing earlier on the other kinds of generative models, there's just getting to be this almost fever pitch of interest in these topics right now that over time we're going to see these branch out into more and more domains. So I'm going to quickly talk about some challenges of GANs, and then we'll have time for some more questions and talk about the course a bit. So I was telling you how we have this nice situation where we have a minimax two-player game. We're just looking for the Nash equilibrium. We pass things through the generator. The generator learns how to have good weights to trick the discriminator. The discriminator stops being good at detecting the difference and starts randomly guessing. It all sounds really, really nice, but in reality, it's not so easy. If any of you have experimented with GANs on your own time, you may have seen a lot of your results come out like what's on the screen. So there are still challenges associated with GANs. And three of the big challenges are mode collapse, finicky training, and evaluation of GANs. This is a perpetually contentious topic. So mode collapse, it's when the data has several modes, but we only learn one of them through our training. So this is a visual example of what that looks like. Now, a lot of work since Goodfellow's original paper has been around how can we deal with mode collapse and how can we prevent mode collapse. An example is the progressive GAN paper from 2017, also out of NVIDIA, where they start with lower resolution images and work their way up to full resolution images in the hopes that the discriminator and the generator are better balanced in this way. Then there's the issue of finicky training. I was talking about the cost functions of the generator and discriminator earlier, and because we have two different cost functions in this model, it creates more challenges in terms of balancing them than you might otherwise have. So a lot of getting your GAN to train properly is getting the hyperparameters right, getting the learning rate right, and really making sure that you have enough data to do what you set out to do. And lots of experimentation. And then finally, evaluations of GANs is by no means a closed topic. Good samples from a generator doesn't necessarily mean you've learned the distribution well. It can be very hard to estimate the likelihood, which is a measure of how well you've learned the distribution. And because of this, it's hard to really know how much of the distribution you actually learned. You might have learned a small section of it really well, but ignored the rest of it entirely. And with images, this is easier to explore, even though with large data sets it's still challenging. But when we look at non-image applications of GANs, this is something that we really want to dig into and understand really well, because it's not as easy to visually inspect the results of non-image applications of GANs. And finally, this how to evaluate GANs is really an active area of research, with most papers that really propose a state-of-the-art architecture. They seem to also propose a new evaluation technique that can make their architecture look really good. So there's still a lot of work that we need to do to, as a generative modeling community, to really converge on how we're going to evaluate these models. And now, so thank you for listening to the GAN presentation, and now we can take questions and also talk a bit more about the course. So I'll hand it back to Xian.
All right, thank you for the presentation. We do have actually I lost count of how many questions. Wait, let's. But it's not that many. It just there's a thread going on. There's a lot of active discussion. So I'm just trying to filter through the talks. So the first question is people are curious if there are applications in the field of healthcare, and as well as maybe architecture and building design.
Cool. So healthcare, very active area of GAN research. There's a lot of work in molecular design done using GANs, and the pharma industry in particular is putting a lot into using GANs to create new drugs and to come up with new pharmaceuticals to deal with different diseases and issues that people are having. So that's a highly active area of research. With regards to architecture, there's been, I can't remember the name of it, but there was a very neat paper published a couple months ago generating floor plans for buildings using GANs. There's also been work with GANs to actually generate, say, components of a structure or pieces of a structure. And then, somewhat related, there's a really cool paper from Adobe at iClear this year, International Conference on Learning Representations. It's a really big machine learning conference. And it was generating graphic design layouts through GANs. So it's a somewhat similar concept to architectural layouts, but in a very different domain. So both those areas are quite active in both research and in industry at this time.
Okay. As you can see, Andrew is a very good at explaining things. He's actually one of the people that I know that can explain concepts really well. And Andrew also, I went to conference with him, and Andrew is very knowledgeable in the field of GAN. Let me try to group these two questions together. Does it take a lot of time to train GAN, and can we train it in Colab?
Cool. Yes, you can train it in Colab. It depends on the size of your data set, the variation of your data set, and the complexity of your architecture. But it is possible to get reasonably sized data sets that create reasonably good examples that you can train in the order of, say, an hour or so in Colab.
Okay. So there are two questions about the workshop itself. So let me get those out of the way. So the first question is, are there any recommended books or recommended material we can read prior to taking the GAN workshop?
So the more background that you have in GANs before you come in, the more effective the workshop will be, because we'll be able to dive into specific questions. Everything that I've cited in this presentation is very worthwhile to read. And in a way, at least for the GANs, the generative model stuff that I cited, if you're interested in that for context, go ahead. but the papers on GANs like Goodfellow 2014, Radford 2015, the papers from NVIDIA by Karas in 2017 and 2018, the Isola paper and the Zoo paper, those are really important ones and build up a lot of the foundation of it. Uh, Reading just a general book on deep learning, like Ian Goodfellow's deep learning book, is a good way to brush up on your skills before you come into it. Uh, and aside from that, maybe just doing a deep convolutional GAN tutorial or two before you get into the course so that you're really familiar with the concepts when you enter on day one so that we can have really great discussions and dig into the nitty gritty of this.
Before we move on to more questions, I just want to make mention that we are having a limited discount of 30% within the next 48 hours. I'm going to send the link to the chat box and Slack channel, so you can use that link. And if you follow that link, the discount is already applied, so you can purchase the workshop with discounts automatically. So actually, the next two questions are sort of like wish list for the workshop. The first one is, can we cover methods of finding the saddle point of the cost functions in the workshop? The next question is, can Andrew cover a bit on using GAN on semi-supervised learning?
Cool. So for methods of finding the saddle point, that can be a tricky topic to get into. And on the last day, depending on how much progress we've all made and the sort of challenges people have encountered and where the group interest is in, that's something that we could dive into. Semi-supervised learning is definitely something on the third day we can talk about, because that is a really active area of research and work right now and has very broad-based applications.
Okay, so can we? Oh, okay, it's the same question. Some people was wondering. You mentioned about the Google paper about using GANs to do translation.
Mm.
Do you mind sharing that later with me, or I can relate it to the on the Slack?
Yeah, absolutely. And to just be clear about that paper, it's using concepts from GANs. It's not directly using GANs, but it's still a very interesting paper. And I'll share that with Xion after this.
Okay. So I think people are still there's still a little questions about, like, some people still don't quite wrap their head. I guess they can't wrap their head around how can a discriminator be trained when it starts with absolutely no knowledge, like start with basically random guesses. Could you elaborate on that?
Is it how the discriminator can be trained?
Yes.
Trained? How the generator?
The discriminator.
The discriminator. So the discriminator, we have a way to evaluate whether the discriminator is correct or not. This is a really important piece of the architecture, because we know whether we send the discriminator a real image or a generated image. So the discriminator is getting gradient signals based on whether it correctly identifies a generated image as generated and a real image as real. And because we know what we're sending into the discriminator, we can evaluate that after it's made its classification.
Okay. I think this is the last question. Any works on interpreting latent space vectors in conditional GANs?
I mean, it's a pretty big area to talk about. I guess what you would talk about in the context of is like what you're trying to find, what you're trying to do with it, and yeah, it would mostly be around like to what end are we analyzing the latent space, and a particular example.
Okay. I think that's all the questions. I may have missed some, but if you have further questions, feel free to ask on the Slack. Um, as was mentioned, I just posted a link, a 30% discount on the GAN workshop. You can use that link to purchase the workshop till around Friday. And Andrew, I know Andrew for a long time, and he has previously delivered the pipe torch tutorial, and as well as he also gave a presentation at ACE. So I know him. I know him as a very good people to explain things and concepts. So the workshop itself will have will be 3 days, covers about 9 modules. So where Andrew will progressively go into, like, first of all, introduction of GANs and get into the very details of GANs. And second workshop will be CycleGAN and how it works and what you can do with it. And the third and in the third part, it will be some advanced concepts such as maybe some techniques and problems, challenges, and maybe and a little bit on the adversarial training in general. So if I can add, my understanding is that adversarial learning and adversarial, or some people call adversarial training, is a very important techniques that we see is being applied to many of the algorithms. And if you go to any of those conferences, we lose track of like how many models have a adversarial components to it. So I think, in my opinion, this workshop is more about GAN, but once you learn the concept of GAN, you will be able to understand like how those adversarial components work in general. So with that, I think we are about running out of time. So I'd like to thank Andrew for, again, delivering this like really great presentation. And thank you everybody for chatting. And there has been a lot of chats today, and some people have asked answered questions. Appreciate that. And if you have more questions, I see there's a lot of people still wishing to carry this conversation. Feel free to chat it on our Slack channel. If you don't know what I'm talking about, please send a message, send an email to us at events@ai.science, and we will give you registration form and access. All right, thank you very much, and thanks again, Andrew.
Thank you, Sean.
All right, bye-bye. Okay, let me end the live stream now. All right, some people say thank you, clapping. Yeah, okay.